So today we have Konstantin Wernli from University of Southern Denmark talking about his recent work on combinatorial quantum field theory on graphs. We are very excited to have him, and the floor is yours. Thank you.
So yeah, thank you, Maziar, for the introduction and also for the invitation. I'm really very happy to present this recent paper here. And it's a paper that I'm also quite happy about. I think there are some neat things there. Yeah, it's a joint work with Ivan Contreras, Santosh Kandel, and Pavel Nyov. So what am I going to be talking about? So here's the one slide summary of my talk. So I'll consider quantum field theory on a graph where the space of fields has just zero cochains on that graph. So it's just R functions from vertices to R. So it's a finite dimensional vector space. And today I'm mostly going to be talking about the partition function, which is this integral here. So we integrate over the space of fields, the exponential of the action functional divided by h bar, and the action functional is right here. So it is given by this formula, which I'm going to explain in a couple of slides. Okay, but so here you can the main ingredient here is the graph Laplacian delta and a polynomial potential p of phi. Okay, and mu, it's just some, it's a zero chain on the graph, so we can pair it with this zero cochain here. All right, and then there are two main results in this paper. So the paper is a little bit eclectic maybe, and it grew quite long, but I think there are two main results that I want to present today. So the first main result is that you can, so this partition function can be thought of as a functor. So we define a graph cobordism category, and the partition function defines a functor from that cobordism category into the category of Hilbert spaces. And there's also a sort of experimental higher categorical version of this statement, and which I want to talk about today. And the second main result, or maybe class of results, is that all the objects that appear in this quantum field theory, or maybe in its perturbative version, they have combinatorial expressions in terms of the graph. So they can be expressed in terms of weighted path counts. So you'll see later what I mean exactly, but I think it's intuitively clear what is a path on a graph. And so all the objects here, they have some expressions where you just sum over all paths in the graph, and you weight them with a certain weight. And why were we thinking about these things? So there were sort of 2 points that we were coming from. And so this is a little bit text-heavy slide. So this was one of our main motivations. And so one of our main motivations was precisely studying functoriality of QFTs. Okay. And so functoriality, it's one way to mathematically formalize this physical principle of locality. So functoriality means that the partition functions of quantum field theories should, or some quantum field theories should define functors out of a cobordism category, which models the space-time. So it somehow means that your quantum field theory is compatible with cutting and gluing of space-time. Okay, and that somehow means that what happens at some point in the universe doesn't know about what's happening at some other point in space-time. And originally these concepts were formalized by Atiyah and Siegel in the late 80s, early 90s. And that was in the context of topological quantum field theories. So a topological quantum field theory, it's something that doesn't depend on the geometry of space-time. And that's if you think in terms of physics, that's maybe something like if you try to translate this into another subject, topological quantum field theories, they're nice, but they're something like non-elephant biology. Elephant biology. So that they're just a very, very special subclass of physical field theories. And the typical field theories that appear in nature and physics, they're not topological. So they obviously depend on the geometric structure. And it's sort of still a big challenge for mathematics to understand them more precisely. And one question that you could ask about these geometric QFTs or non-topological QFTs is precisely whether there is some sort of functoriality that they satisfy. And that was put down in 2011 by Stolz and Teichner. There was a proposal of a cobordism category of Riemannian manifolds, and that is sort of the version that we were inspired by. And there are still like very few examples of functorial field theories that depend on the geometry of spacetime, so geometric functorial QFTs. And most examples are one-dimensional, so essentially some version of quantum mechanics. And I put some names on this slide of people who of recent names, I think. Yeah, so some people would say that one-dimensional functorial field theory goes back to Dirac. Okay, but so here are some recent names. And another class of theories where you can build those functorial field theories in the geometric setting is free theories. So theories where there is no potential. And actually, Santosh Kandel was a student of Stefan Stolz, and in his PhD thesis, he defined sort of one version of the free theory of the version of the theory that I'm talking about today. So he defined the functorial version of the massive scalar theory. And then there are also some other people that defined functorial theories in the free setting. And so a couple of years ago, together with Pavel Mjov and Santosh Kandel, we looked at the interacting massive scalar theory, and we showed that the perturbative theory is functorial. So you look at the perturbative partition function, which is built, from the zeta regularized determinant in Feynman graphs, and you look what happens when you cut and glue the space-time manifold. And this was only on two-dimensional manifolds. And already there we ran into this problem that you need to, so in the geometric QFTs, you need to renormalize. So in most topological theories, you don't need to renormalize, but in geometric QFTs, typically you have divergent Feynman graphs, and you need to think about how that interacts with gluing. And in 2 dimensions, there's only a single Feynman diagram that is divergent, which is a short loop. And already that gave us some headaches. And so one reason to write the paper that I'm talking about today is to sort of, analyze this problem in a simple setting. Just like, okay, it's a very hard problem. I think it's an important problem. Many people are working on it. And so we just wanted to have a setting where we could get some actual results. So that was our first main motivation. And then The second main motivation was this idea of the first quantization formalism. So the perturbative partition function is a sum over Feynman graphs, and the weights of the Feynman graphs are given by integrating products of Green's functions. And the Green's function is sort of, you could think of it as a second quantized object. That's sort of some physics speak. But in the written on the slide is a sort of first quantized formula. And that just means that you write the Green's function as itself as a path integral. So it just sort of, so the Green's function just sort of intuitively tells you, okay, like a particle is going from point X to point Y in space-time. And you can write this Green's function as sort of an integral over all possible ways the particle can travel from point X to point Y, and integrate over all possible times that it can take. And that gives you another way to sort of think about quantum field theory, which is sometimes called the first quantized version of quantum field theory. And again, those path integrals, they're just mathematically hard to handle. So maybe you can make sense of them, but it's very difficult. And again, we just wanted to study this in a setting where we could actually, write down some formulas and prove some theorems. So and some versions of this already existed in the literature, and we just sort of developed this further. Like we looked how everything interacts with cutting and gluing, and I think in this process, sort of we have this new formulas for the Poisson and Dirichlet to Neumann operators on the graph, and they're like continuum analogs. I haven't seen in the literature, but I mean maybe they are somewhere. But so I think sort of in this way maybe we have arrived at some new nice formulas. Okay, so this was this was the second part of the motivation, and so maybe it's already first good time for questions. So after this, the talk will get more elementary. So this was just to say why we were doing what we were doing. Okay.
So just
Yeah.
a small question. This model is for a particle on a Riemannian manifold, right? Like
Yes.
the action that the Green's function. So it's like I can think that I have a particle on a Riemannian manifold, and this g of xy is telling me what the probability of this particle going from point X to point Y for any time is. Is that kind of the intuition?
Yes. Yeah. Like yes. So just the probability that it goes from point X to point Y in some proper time. And you can sort of decompose it into all possible times it could take to go from point X to point Y, and that's what's the integral on the right-hand side is doing.
I see. Okay. Thank you.
And then like the inner integral, the integral over paths, that's sort of the path integral from quantum mechanics. And so in physics, there is this idea that like the first quantization is from classical to quantum mechanics, and then the second quantization is going to quantum field theory. That's sort of oversimplifying it, but that's where this name comes from, like first quantization formalism. So it's just that we are thinking sort of in quantum field theory, the particles can be annihilated and created, but in this first quantization formalism, you're thinking about quantum field theory from the viewpoint of the particles. Yeah. Anyway.
And so, sorry. So if you think about quantum mechanics, like having a scalar field doesn't mean anything, but then because you like quantized again, then you have these scalar fields coming in. Is that where you bring them in? Like when you have this, yeah, I guess like my confusion comes from like I don't know when you have a quantum mechanics, and I don't know when you have a quantum field theory.
So yeah, so if you go to a QFT course, then sometimes like that was what happened in my QFT course. Then you quantize some classical system, and then you arrive at some wave equation, and then you sort of quantize that wave equation again, and then you get quantum field theory, and that's why it's called like first and second quantization. And that's maybe a sort of, I mean, it would take a while to explain now, but sort of in
Okay,
our approach, we were coming from quantum field theory. We are trying to sort of go back to quantum mechanics. So
I see. Okay,
you're thinking, okay, in quantum
makes
field
sense.
theory, like what happens? Like a particle is created somewhere, and then it goes to some other point, and then it interacts with some other particles and dies. And so, like in this formula here, you're expressing this Green's function that you're putting in a Feynman diagram from the viewpoint of the particle somehow. Like an actual physicist is probably going to strangle me right now, but I mean that's sort of more or less my understanding. Okay. Um, okay. Right. And so some previous work that we use in this text. So there's a paper by Reshetikin and Wertmann where they essentially considered the same model, but only in the free version, so without the interaction potential. And they also focus only on the gluing formula for the determinant and not so much on the Green's function and nothing at all on the first quantization formalism. And so Pavel Mnyov, he's been working on these combinatorial problems also for a while. So there's a paper on Selberg trace formula from 2007 for regular graphs, so when all vertices have the same valence. And then he has this note in sort of notes of the Max Planck Institute on graph quantum mechanics. And some of these have some formulas that I'm going to come back to in a while. They were in a master thesis around 10 years ago. But I think most of it was sort of never like collected in one place and written up. And we also considerably expand all these paths and formulas and show precisely how they interact with cutting and gluing. Yeah, that was our contribution. And then there is our paper from, well, I think it was finished 2019, and then it's an ATMP 2021 about this functoriality of two-dimensional perturbative massive scalar field. And that was, I think, also a major motivation, because I think we were trying to sort of extend the results in that paper to, so for once we were trying to extend them to corners, and we were trying to extend them to higher dimensions, and sort of got a bit stuck. And so we decided to try something simpler and work with graphs. And with graphs, it's just like everything works. So it's really cool. Okay, so let me get to the main part. So I'm going to talk a bit first about the model itself. And I'm also going to briefly mention like one version of continuum limit in the simple case of where it's one-dimensional, where everything is sort of an exercise and you don't need to think about things. But in one dimension, we already see that you get like the massive scalar QFT back. So that's a good sign. And after talking about the model, I'm going to talk about the functoriality and the path sum formulas. By the way, is this talk like, is it, so on the website it said 90 minutes, but is it really 90 minutes or is it more like 60 minutes?
Hi, Konstantin. I didn't get a chance to say hi to you. Thank you for
Hi,
doing this.
Marco.
And,
Yeah.
definitely, you can use 90 minutes, and you can probably go more if necessary.
Okay. Yeah, I think I have enough stuff, but you can stop me at any point.
Okay. Okay, yeah, but
All
there's
right.
no rush. Yeah.
Okay. Okay, good. So let's get started with this. So our spacetime is a finite unoriented simple graph. So And I'll denote the vertices by Vx and edges by Ex. And okay, I put here some random picture of a graph to just tell you that in principle, that the graph is arbitrary. Okay, it doesn't need to look like anything. It doesn't need to look like a manifold. It can just be your favorite graphs. A simplifying assumption that we use is that there are no multiple edges or short loops, but you could do away with that. I think you could probably weigh every edge with a real number, positive real number if you want. And short loops, they sort of essentially just drop out of the model more or less by definition. But just to keep things simpler, we work with this assumption. So some graphs are deregular, which would mean that all vertices have the same balance. So obviously, this graph is not regular, and we don't need regularity. It's just that for regular graphs, some of the formulas simplify. But actually, also one thing that, that's sort of also something that we figured out is that we don't need to work with regularity. Like we don't need this assumption to write down our combinatorial formulas. So we found new formulas that work for non-regular graphs. All right, so some basics that you probably saw last week, because I saw Mathiar already gave a very good talk about this. So the adjacency matrix of a graph, it's just a matrix that has rows and columns labeled by vertices, and its entries are either 0 or 1, depending on whether there is an edge between the two vertices or not. And if you feel like it, you could probably replace that 1 with a real number that depends on the two vertices. But for today, we will just keep this version. And the graph Laplacian is also a matrix whose rows and columns are labeled by vertices. And it's the difference of the degree matrix and the adjacency matrix. So the degree matrix or valency matrix, it's a diagonal matrix, and its its entry is just the valence of a vertex. Okay. So rows and columns are labeled by vertices, and it's the entry at the u equals 2b place is just the valence of that vertex. And if the graph is regular, this is a multiple of the identity, but otherwise it's just some diagonal matrix. And then the entries of the Laplacian in this version are just the valency of the vertex on the diagonal and -1 if there is an edge between two vertices and 0 otherwise. Okay, so here are some examples. So this first graph is a two-regular graph. So the graph Laplacian, which is on the right, is just like 2 times the identity matrix and then minus this adjacency matrix. And then there's if you look at line graphs, they are not regular. And so you can just see the Laplacian here. And you could also, like these are graphs that sort of look remotely like manifolds. Okay, so this looks like a very much discretized circle, the first one, and the second one looks like a very much discretized interval, but the last one is not really anything in that direction, but it would be perfectly fine to use as a space-time for us. Okay, so now let's get down to what the model is in detail. So the space of fields is just a space of functions on the vertices. And so that's just like a finite dimensional real vector space, because we assume that the graph is finite. And then the action function is written below. So on this vector space, I have a standard inner product, just a canonical inner product on R to the n. And then, okay, I just pair phi with the Laplacian plus m square phi. So m is just some real number. And then I add this term where I pair the standard zero cochain mu. So by standard, sorry, I think it says a typo here. It should be just zero chain. So it's just the sum of all vertices with coefficient 1. And what it means, you can see in the next line, it's just you add p of v of phi for all vertices. And so the first term of the second line you get when you sort of expand the Laplacian and do some manipulations. Okay. And then the first term of the action function, that's sort of the free part or Gaussian part. And the second part is the interacting part. And so we assume that our polynomial starts in degree 3. Okay, so the first term is quadratic. The second part is cubic and higher. And there's no linear term. And we assume that there are finitely many terms in this polynomial. Okay. So that's the action functional. And so first we'll look at closed graphs. So closed graph doesn't really mean anything, but what we're going to do later is that we're going to consider X together with a subgraph, which is a full subgraph. So it just means you take a subset of the vertices and all the edges between those vertices. But if that subgraph happens to be empty, then we say that the graph is closed. Okay, so in analogy with a closed manifold. And then we define the partition function to be just the integral of the action exponential of the action functional over this finite dimensional vector space. And we assume that our polynomial is such that this integral converges absolutely. So for some polynomials, this integral might not converge, but we don't want to consider those. We want to just take polynomials where this converges. So for instance, you could take phi to the fourth, but not phi cube, I think. And we want, okay, and one thing that I didn't write is that we require that the action function has a unique critical point at 0. So that's also an assumption on the polynomial. Okay. And for now, h bar is a finite positive number. Okay. So that's the partition function. And for, when p is 0, then this integral is Gaussian. So that's why it's called the Gaussian theory. And then the partition function, we have normalized the path integral measure so that it's just the determinant of this kinetic operator. Okay, so we call kx the sum of Laplace x plus m square. And you can just, in that case, the integral is just the determinant. So in that case, you know the whole theory if you know the determinant of the kinetic operator on this graph. And sort of for small matrices, that's just something you could give to a first year undergrad probably, or so for 3x3 matrices, you can just compute it by hand. And then in the paper, we have some examples where we compute this for, I think, circle graph on n vertices or a line graph on n vertices. But in general, it's not that easy to compute, actually. If you don't know anything about the graph. I mean, it's sort of as hard to compute as a determinant of a matrix the size of vertices in general. Okay. So if the polynomial is not 0, then we don't really have a closed formula for the partition function, but there is this closed formula for its asymptotics, and that's called what we call the perturbative theory. So when h bar goes to 0, then this is sort of standard results in analysis tell you. So the integral diverges when h bar goes to 0, or like as a function of h bar. And this goes to infinity when h bar goes to 0, but the question is how does it go to infinity in some sense? And you can say that very precisely. So, and the answer is here. So you still have this overall factor of 1 over the determinant. And then the behavior in h bar is given by this sum over finite graphs. So that's one way to get the combinatorics of this. So you sum over all finite graphs that have that are at least trivalent. You weigh them with h bar to minus the Euler characteristic of the graph and divide by the number of automorphisms. So that's just some combinatorial factor. And then the weight of the Feynman graph is given by this formula here. So to every vertex, you just associate that coefficient of the polynomial. And to an edge of this Feynman graph, you associate a Green's function, okay? And then you have to sum this over all possible ways to embed the Feynman graph in the space-time graph. So I think I have an example a bit later in the relative theory. So that's how you define this weight. And one other thing why I was sort of happy to study this finite dimensional model is because, I mean, usually when you work in perturbative QFT, you sort of use this as a definition of the Feynman path integral. It's one definition. It's like the perturbative definition, because this is a formula that you can always write down, apart from troubles with renormalization and things like that. But you can always write down this formula, whereas this integral here, like the partition function, the integral itself is usually not defined. But in this case, the integral actually is defined, and its actual asymptotics is given by that formal power series. So here we have this formal power series, which has just like a completely combinatorial expression. And all the ingredients in this power series are the determinant of the kinetic operator and the Green's function of the kinetic operator. So in principle, you can just calculate it explicitly if you want. Yeah. Okay, so yeah, then that was sort of all I was going to say about closed graphs. So if there's any question before I start with the relative version. Okay, so I think my main point here was just that to know the perturbative version of the theory on a closed graph, I just need to know the determinant and the Green's function of the kinetic operator, so that these are sort of two objects that we're interested in. Okay, so now,
sorry,
yeah.
Konstantin. So I think on the previous slide, so you somehow said that this z of h, the non-perturbative partition function, explodes as h goes to 0, but it actually doesn't. I think it has a constant sort of limit, and then sort of it doesn't explode, right? It's actually, it has, for h positive, it has a power series. So yeah.
Because the critical value is 0, right?
Yes.
So typically you would have like 1 over h bar term, like
Oh,
exponential
right.
1 over h bar times the critical value, but you're
Yes.
probably right that the critical value is 0 because we're assuming that.
Right.
Mhm.
Yes.
You're speaking about the actual partition function as a function of h bar that has an essential singularity at h bar is equal to 0.
Yes. Yes.
So you're saying that it's like flat in the positive
Yes.
half plane, and then it's highly singular in the left half plane. But,
That's right. That's right.
yeah, but it will have asymptotics and well-defined limits in the right half plane. Yeah,
Yes.
okay. Right.
Yeah, so I think for a general QFT, I think it blows up, but that's because the leading term is well, exponential of the action functional evaluated at the critical point over h bar, but here the critical point is 0 and the action functional vanishes there. So that's why the integral, the limit is finite when h bar goes to 0 along the positive reals, as you said. Okay. So let's go on here. So we could take a graph and then take a full subgraph of that graph. So that just means we take a subset of the vertices and all edges between them. And then it turns out that we slightly have to modify the definition of partition function. So now we want to think of the partition function as a functional of the boundary values of our field. And so I'll say boundary values because typically we think of y as a sort of boundary of the graph, but it's purely intuition. Like y could be any subgraph of x. It could be x. It could be empty. It could be some isolated point somewhere in the graph. But I'll typically call it the boundary because that's where we are coming from. So the partition function depends on the values of the field. Sorry, it's a function of the values of the field on y. And so to define it, we just integrate over all fields that restrict to this boundary values, but we sort of slightly modify this the integrand. So instead of integrating action functional over h bar, we subtract like 1/2 the action functional of y. And that's because that this is sort of some artifact of this discrete theory that's necessary for gluing. And that would vanish in the continuum theory.
Are you going to say more about this correction later?
Yes, yeah, I think in a couple of, well, I think in the proof of the functoriality.
I'm just wondering if, like, when you were developing this, do you have a way of thinking about that correction factor as some kind of trivialized cocycle somewhere? Do you have some way of understanding what it is?
I think the way to understand what it is that we want the action functional to be additive when we take union of graphs along subgraphs.
Yes.
So if you take two graphs with some like the same y
Yes.
subgraph, and well, you take the union of those two graphs along that graph, and you add the two action functionals, then you sort of overcounted y.
Yeah.
Because you're summing over all vertices, right? So you need to sort of subtract the action
It's
function of
clear,
y again.
From that point of view, wouldn't you say that there's other ways that you could have solved that problem in a way? Like, could you have put different amounts on different sides?
Absolutely, you could.
Yes.
Yeah, if you split things into ins and outs, you can split this sort of differently between ins and outs.
Right. So I'm just curious, like, I'm just wondering if there is a better way of thinking about what this is. Like, why is this occurring? I mean, I assume that it occurs in the continuum theory in some sense, no? I mean,
yes. So I think one way is one can reshuffle sort of this extra term and reinterpret it as a part of the Hilbert space structure on HY.
Yeah.
Yeah.
I think that's what's Vershetikin and Wertmann did, right?
You mean you
And
change
also what-
you mean you change the integral measure to include the SY?
Right, right.
Yes. Yeah, so yeah, I didn't say it, but yeah, here in this L2, right, so the zero of y is just some Rn, and I'm just using the Lebesgue measure in this L2. But what Pavel says is that you could absorb this Sy into the measure in that L2.
But then it would be with a positive sign. It would be e to the plus SY over h bar.
Would it, because wouldn't that make it badly behaved?
I guess you have to pick the opposite contour somehow. Okay, sorry, I don't want to derail you. Continue.
No, it's fine. It's fine. But I mean, yeah, I think just if you want convergence, it seems like you want. I mean, you want interesting things in your Hilbert space. It seems like you want to have negative exponentials of negative things, not positive things. But I don't know. I would need to think a bit more.
Okay.
But yeah, I can say that in this other paper with Pavel and Santosh, where we talked about the continuum case in 2D, we also somehow, we absorb some parts of this term into the Hilbert space structure, I think. So yeah, that is a game that you need to play somehow. But here, like
it reminds me a little bit of anomalies, the theory of anomalies. But I guess here it's some kind of simpler version. But there is no you don't have some secret higher level way of thinking, conceptualizing this modification. It's you're putting it in because it works. It makes everything functorial.
Yes, yeah, and I think that it's simply because if you're like taking this union of graphs, then you're just overcounting y. So that's how I understood it. I don't know if Pavel has a secret higher interpretation.
No, I don't. I'd like that, but I don't. It doesn't quite look like this sort of in this continuum setting. We had an interesting Hilbert space structure or for space of states on a circle, but that was more like partition function of a semi-infinite cylinder. So it was coming from that. It was this sort of root of Laplacian plus m squared on the circle. So this one half SY doesn't look like anything related to semi-infinite cylinder. So yeah, here I don't know how to interpret it that way.
It also reminds me of the way that they do Morse theory on manifolds with boundary, where you have half contributions from the critical points on the boundary.
That might be some similar mechanism, but yeah.
Because that's where usually the Morse function appears exactly up there in the action. Anyway, okay, maybe we can discuss later. Okay, bye.
No, thanks. That's actually an excellent question. So yes. So if we have a graph with a subgraph like this, then we sort of have a discrete version. So what am I trying to do here? Yes, I'm trying to find the explicit formula for the free theory again. So we assume that P is 0, and then we want to find the explicit formula. And to do this, we need to study this Dirichlet problem, where like we are looking at those fields that restrict to our boundary condition, and then we are trying to solve this equation that the kinetic operator annihilates the field. And to do that, okay, you can write the inverse of this kinetic operator as a block matrix. So separating vertices that in X take away Y and Y. Okay, so A block is like XX vertices, D block is YY vertices, and so on. And then it turns out you can just explicitly solve this equation with this boundary condition. So and then okay, this solution, like this operator that gives us the solution from the boundary condition, we call it extension or Poisson operator. And that's like very common thing in PDEs. So, like this one. And the second object that we need is the combinatorial version of this Dirichlet-to-Neumann operator. So Dirichlet-to-Neumann operator in the continuum setting is defined as follows. So you take a boundary condition, and then you solve the sort of this Dirichlet problem in the bulk. So you find the harmonic function with that boundary condition, and then of this harmonic function, you take a normal derivative on the boundary. And then you sort of get the Neumann boundary condition that gives you the same harmonic function in the bulk as the Dirichlet boundary condition that you started with. And so in our case, we don't have this interpretation because Y is typically not an actual boundary, but it turns out that sort of this D inverse, it's the right combinatorial version. Okay, so you simply look at this block in the inverse of the kinetic operator, and then take inverse of that again. All right. And so then with this Dirichlet-to-Neumann operator and the sort of relative kinetic operator, which is just the x block of the kinetic operator, you can write down a formula for the partition function of the free theory on like relative to a subgraph Y. Okay, and then like this Dirichlet-to-Neumann operator appears here. Okay, so it's 1 over square root of the determinant and then exponential of the Dirichlet-to-Neumann operator minus this kinetic operator on the boundary. And this kinetic operator on Y, it sort of comes from this correction term here. Okay, but again, like I want to make the point that you can express this partition function by just knowing like the determinant of this relative kinetic operator and the Dirichlet-to-Neumann operator. Those are the two ingredients of the free theory on a graph with boundary. And okay, here are some examples. So if you look at this 2-vertex graph and you take one vertex as a subgraph, then okay, like there's only one vertex which is in X but not in Y, and there's only one vertex in Y. So like this determinant is just the corresponding entry of the Laplacian. Okay, so the vertex 1 here has valence 1, so that's where 1 comes from, and then you add m square. And okay, then this Dirichlet-to-Neumann operator, that's a computation that you can do in a couple of minutes. And then we actually computed also the explicit answers on these line graphs of any length relative to 1 or 2 endpoints. And then just mentioning these formulas because then in a second I'm going to look at the continuum limit of an interval, and then those formulas, they will sort of converge to the almost in some sense to the formulas in the continuum theory. Okay, and so here there appears this parameter beta. So you sort of solve this by making an ansatz, and then it's convenient to write it in terms of beta. Okay, and also in the relative case, you can write down sort of a perturbative partition function. So again, like the actual integral for h bar positive might be very hard to compute, but you can always write down a formula for its asymptotics as h bar goes to 0. And it looks essentially the same as in the closed case, but now Feynman diagrams sort of they have two types of vertices, bulk and boundary vertices. And the vertices between bulk and boundary edges, they are decorated with the extension operator. So it's probably best to just look at the picture. So here I have so this is a Feynman graph in the left. And to evaluate the weight of this Feynman graph, I map it to the actual graph X. So here X is some sort of lattice, and Y is the boundary of that lattice. And so here, if I denote, like I have to sum over all of these maps of the vertices of the Feynman graph, two vertices of the spacetime graph that respect like this bulk boundary decomposition. So the bulk vertices of the graph, they have to be mapped to the bulk of the spacetime graph, and the boundary vertices of the Feynman graph have to be mapped to the boundary vertices of the spacetime graph. And then, like if you have an edge between two bulk vertices, you would associate the relative Green's function. So that's just the inverse of the relative kinetic operator. And if you have an edge from bulk to boundary, you would associate this extension operator. So in some case, that's the bulk boundary propagator. It's another way to call it. And so here is just the explicit formula. And so there's like square of this relative Green's function, and then two different bulk boundary propagators. And the vertices, from the vertices, you get this P3 squared, so the cubic term of the polynomial. And on the boundary vertices, you put this, I see there's a Y missing here on the right-hand side. So like this, so this Feynman weight is a function of the boundary values of the field, and they enter here on the very end. Okay, so that was the perturbative theory in the relative case. And so again, like the point that I'm trying to make is that like there are four ingredients here. So now there's a determinant, there's the Dirichlet-to-Neumann operator, there's the extension operator, and the Green's function. So those are the four objects that appear in the perturbative partition function in the relative case. And if we get there, I sort of have combinatorial formulas for all of them. Okay, so now let's just, this is a small aside where I'm looking at continuum limit of in the one-dimensional case. So, and I'll do this only for the free theory. So we look at an interval of length L, and there, so this action functional here, it's just the action on this finite length interval, okay, of the free theory, continuum free theory. And I can write it as the limit of a Riemann sum, like here. And so here, I think that I'm dividing my interval into n points, and the distance between those points is epsilon n. And so this formula here, this is precisely the action of our model on a line graph with n vertices. Okay, so by sort of writing the Riemann sum for this action functional, you recover the discrete theory. And the important thing is to see how the parameters are scaled. So the mass is rescaled with epsilon, and then the kinetic operator is rescaled with epsilon inverse. Okay. And then we can use that to look at the objects that we computed in the free theory, do that rescaling, and try to take the limit, and then compare with the continuum theory. Okay, so So for instance, we can look at the Dirichlet-to-Neumann operator that we obtained in the discrete theory. So let's have a look at this formula. So that's the formula in the lower right corner here, okay? So beta for small values of m, so we scale m with epsilon, which means that beta becomes almost m, and beta times n, that becomes m times the length of the interval, okay? And so, and like cosh beta, that goes to 1, and here this goes to something like cosh ml. And then you recover this operator here, which is actually the Dirichlet-to-Neumann operator of the continuum theory, okay? Which is actually an example that we computed in our 2019 paper. And so for the determinant, it's a little more interesting because if you do the same game for the determinant, so first of all, there's a scaling factor. So the determinant goes to 0, which is to be expected because when you send m to 0, the determinant just goes to 0. And so it goes to 0 with a certain power of epsilon. But then something that I personally find interesting is that it actually doesn't give you exactly the same as the zeta regularized determinant. So it's off by a factor of 2 here. And if you did the same thing for a circle, which is what I did on this slide, it's not off by a factor of 2. You get the same thing on the nose, okay? And so what it means is that this zeta regularized determinant that we use in the continuum theory, it's actually, well, it's sort of a different regularization from this lattice regularization, if you want. And as we will sort of see in like a couple of slides, that this lattice determinant, it always satisfies the gluing formula. Like the graphs doesn't know anything about dimension, so they always satisfy a gluing formula, these determinants. And the zeta regularized determinant, like it does have a gluing formula, but it's a bit more complicated. I think only in dimension 2, it's a formula on the nose, and in other dimensions, there are some corrections when you glue. And so maybe these results suggest that like lattice regularized determinants glue better than zeta regularized determinants.
Could you go back a little bit and discuss the limit again? So scaling is the thing I need to understand. So you had a, so I'm not sure which way you want to describe it. As a sequence of graphs that are approaching the continuum, what has to scale in which way?
Yes, so I think the idea was that like you look at, you want to approximate the action functional via Riemann sums, right? And so to define this Riemann sum, you take your interval and you divide it into n small intervals of length epsilon. Okay. And so epsilon times n is equal to L, but n goes to infinity and epsilon goes to 0. Okay. And
you mean that capital N goes to infinity, epsilon
yes,
to 0, and L remains fixed.
L remains fixed, exactly.
Yeah. And then what about the other quantities? What do you mean when you say the mass is rescaled?
Yeah, so you want to think of this as a the action functional of a line graph in the model that we discussed previously. But it's not exactly that. You have to do this rescaling that I mentioned. And only then would you get like the action functional of a line graph. So it's the action functional of a line graph with this rescaling.
But what about the implicit metric that is being used on the line graph, like the weight of each edge?
Yeah, I think that is just one still. So the actual metric on the graph doesn't change.
But the kinetic operator is rescaled.
Yes,
So
that's
the
right.
Laplacian is being changed. So implicitly implicitly the metric on the graph is being changed.
Yeah, maybe you could think about it this way. Yeah.
Yeah. No, this rescaling of mass is exactly because sort of we were using the sort of this metric that assigns one to tiny intervals. So it uses the graph, kind of the standard graph Laplacian plus sort of m squared, and we wanted to compare it to delta, which is actually continuum delta plus sort of m continuum squared. So then
Yes.
then there's an epsilon between m continuum and m graph. So we want
kinetic energy, the kinetic operator, what's the relationship between K and the graph Laplacian? The K is not exactly the same as the graph Laplacian. It involves this degree, right?
No, K is the graph Laplacian plus m squared.
Yeah, K is the graph Laplacian plus m squared. The degree part was just the diagonal elements of the graph Laplacian.
So why is m scaling as epsilon and K as epsilon inverse?
So let's see. So if there were the correct sort of the correctly scaled Laplacian should contain like well, second order difference is divided by epsilon square plus m squared. So we kind of multiply everything by so to compare to the graph Laplacian, so you multiply everything by epsilon squared, so you have delta standard graph plus epsilon squared m squared. So that's why epsilon and m somehow go together. So one should probably say that there's like m graph of epsilon and m continuum. So m continuum is fixed. M graph of epsilon scales as Konstantin wrote. So so m graph of epsilon.
What about the epsilon at the beginning of the formula? Like limit n goes to infinity, sum, and you have epsilon over 2 times the thing that plays the role of the kinetic term.
So that's a part of dx. That's a Riemann sum.
Oh, I see. Okay. I see.
So in some sense, yeah, that's maybe mesh size or something. I don't know.
Yeah, exactly. Spacing.
Okay. All right. Sorry. Thank you.
No, don't be sorry. So yeah, this is the only examples for which we actually do this computation. So I think, yeah, one of our main dreams or hopes would be to do this for like more in the higher dimensions, but I think it would be considerably more difficult, in particular in the interacting theory, because then we need to sort of think about renormalizing as well. Okay, so I can see from the way that this is going that probably I'll just talk about functoriality and then maybe stop there, because it's already, but it's fine. So when we think about graphs, so we think about this cobordism category. There's here's how we define it. So the objects are just graphs, and then a morphism is another graph which contains 2 graphs as disjoint subgraphs, and composition is just given by taking union along such a subgraph. So there's an example in the bottom of the slide, which I think tells you how these things work. And the functor is given by associating to an object just L2 with Lebesgue measure on, functions on the vertices. So it's L2 of like some finite dimensional Rn. So in particular, it's infinite dimensional space still. Okay, so and on morphisms, you take sort of the linear map, like you just take this partition function and reinterpret it as a linear map. Okay, so yeah, it's written. So the formula is here. So what do you associate to a function on the in boundary? Well, it's essentially a vector. Sorry, it's an L2 function. And you integrate that L2 function and multiply it with the matrix elements of the partition function. And again, in the integral kernel, you have to subtract these 1/2. Though, as Pavel said before, you could weigh in and out boundaries differently. Just when you glue, it needs to add up to 1, right? So, for instance, we could just not subtract 1/2 for the in boundary and keep it all on the out boundary, or just change just the sum of these two coefficients has to be 1. And in this way, it's symmetric and it coincides with the relative version from before. And then in that case, sort of you have to show that composition of graphs corresponds to composition of linear maps. And we have to use this formula on the top. So the action functional of the glued graph is the sum of the action functionals on the original graphs minus the action function on the interface. So we were sort of overcounting the interface in this sum, and that's why we have to subtract it. And that's why we have these factors. Why you have to subtract these action functions on the boundary. Okay. And that's essentially the essence of the proof. And it is, the nice thing is that it's really like this proof is modeled on the intuition why partition functions should be functors. Like partition functions should be functors because of the Fubini theorem for the path integral. Okay, but so usually the path integrals don't have any Fubini theorems, but in this case, we have Fubini, and then we get functoriality. And so now what's interesting is sort of this extended version that we came up with, in particular because that's some direction which for geometric quantum field theory is sort of really unexplored, I would say. I think that there is some recent work of Grady and Pavlov that I also mentioned in the introduction that claim to have some geometric version of the cobordism hypothesis. And I think that sort of is very difficult to understand. And here we have a more concrete sort of extended version of this functor, but it's, I don't know, I would still say that it's sort of experimental version. Okay, so it's one version of an extended functor that works. And it's probably not the ultimate answer. And also what we're defining is not, so in the extended case, we want to sort of look at some extended cobordism category. So some cobordism category with corners and higher codimension submanifolds. And that should sort of be some version of an N category, but I'm not sure how much this has been fleshed out in the Riemannian context. But in this paper, we define a partial version of an N category. And that means that, okay, we have 0 morphisms, 1 morphisms, all up to N morphisms, but you can only always vertically compose morphisms. So you can always compose K morphisms along K minus 1 morphisms. In particular, you can't compose 2 morphisms along objects, for instance. So I'll show an example in a bit. But so the idea is to just sort of iterate what we had before. So before we just had disjoint subgraphs of a graph as objects. and so a graph with two disjointed subgraphs as morphisms between two objects. And now, okay, our objects are still graphs. And oops, sorry. And one morphism is the same. So it's a graph with graph embeddings as disjoint subgraphs. And higher morphisms, so it's a bit more complicated because there's an assumption on the embeddings. And so the assumption is that the embeddings now can intersect, but they should intersect only in images of the one level lower graphs. Okay, so it's probably impossible to understand this without looking at an example. So here in this example, there are two objects, A1 and A2. And then there are two one-morphisms between A1 and A2. Okay, Y1 and Y2. And they intersect, but they only intersect in A1 and A2, and we don't want them to intersect anywhere else. Okay. And then, so we could sort of, this is a two-morphism, and we could compose it with another two-morphism from Y2 to Y3. And then, okay, that would give the two-morphism on the right-hand side. Right, so here we're sort of taking the graph on the right and we're stacking it on top of the graph of the left somehow. We're identifying this Y2 here or this Y2 here. And then it's just regular gluing of graphs. And like we couldn't glue along, like A1 and A2 are the same, but if we glued these graphs, let's say along A2 and A1 here, like horizontally, like regular horizontal composition of two morphisms, then like these one morphisms, they would actually intersect in that point where we glued over. So they would violate this assumption from the previous slide. So that's why we don't have horizontal composition, just vertical composition. And in that way, it looks more like an actual cobordism category. And then in this case, like the target category is also different because we no longer take Hilbert spaces, but instead we'll take commutative algebras. And that's because they sort of have this nice higher categorical structure where like sort of at the top level, we consider morphisms to be linear maps of algebras. So this is in the third bullet point here. And morphisms from level 1 to n-1, they are just embeddings of commutative unital algebras into each other. And then such morphisms are composed with the balanced tensor product. Okay, so it's a version of an n category. And concretely, so it looks a bit messy, this slide, because I try to put all the details, but concretely what we're doing is that we're associating C infinity functions, okay? C infinity functions on vertices. So those are all algebras. And we do this sort of up to level n-1. And from level 1 to n-1, you have these injective algebra maps, which are given by essentially double pullbacks. Okay. And so, yeah, so this is the reason why you can take L2, because so this is a function on function. So when you're extending it, or like the image of this pullback, it's sort of functions that are constant along several directions. And yeah, they will never be square integrable. So we can take L2, and also L2 functions don't form an algebra. So we do this at all levels below n, and at the top level we take the partition function that we had before, and that's the linear map. And this is like our higher categorical version. Okay, like this may be a bit much to sort of take in 2 slides, but
sorry, could you say
yes.
again, this functor that is taking values in algebras, this is
Yes.
supposed to be the algebra of observables, quantized or classical? Which one is it?
Good question. So, I mean, in that case, I think it's simply you could say it's the classical algebra of observables.
Mm-hmm.
But we didn't think about it this way, I think. Yeah, the point is just to have
You wanted to have some kind of linear target for this.
Yes.
So that you could use Z, the relative partition function, as a morphism.
Mm-hmm. Yes.
So on one hand, it's supposed to be kind of spaces of states, like space of states for the boundary, for the corner, and so on. But on the other hand, it is sort of observables, but like observables that depend only on the phi field, not like you could imagine observables depending on phi and like the momentum field. So here there's no dependence on momentum field.
Yeah. So in some sense, it is like
it's special observables. You could say it like that.
Yeah, or you could think about it as a geometric quantization of like a space in some sense. Like if you add to the phi field its momentum, which you would do in the continuum theory because it's a second order theory. So in the phase space, you would have both like the phi field and its normal derivative, at least on the boundary. And then if you like geometrically quantize this, then you end up with functions only of the phi field. But on the corner, yeah, I don't know. I think then we also sort of just, I mean, it's also a version that works somehow. I don't know. But
the fact that you are using the relative partition function or the partition function as part of the target, I mean, as part of the functor, it suggests that it is quantized. So I'm just curious, why are these commutative algebras?
So there is kind of this model for what should be the target category, let's say 2 extended field theory. So one of the usual models is to put algebras at the corners and bimodules to codimension 2 corners, bimodules at codimension 1 arcs, and morphisms of bimodules in somehow codimension 0. That's one model. And then you're supposed to sort of put some sort of, I don't know, higher deloopings of the category vect. You use them as your target higher category. And we came up with just some sort of replicating pattern where instead of talking about sort of higher, I don't know, higher version of having algebras and bimodules, you have sort of algebras commutative algebras at each level, and sort of 2 algebras that map from the corners into it. They kind of serve as so you have sort of a big algebra for a codimension k-1 object and 2 algebras coming from codimension k boundaries, and it looks like a bimodule over those 2 algebras coming from its boundaries. So it was some sort of an attempt to construct some simple target category. But I think one interpretation of it is observables depending only on the phi field, but phi field where. So if you are on the appropriate part of graph, which is.
I see. You're saying that it's a subalgebra of commuting observables somehow.
Yes.
Which
exactly.
You can, and it somehow you can globally find this algebra of commuting observables. Somehow it makes sense on the whole graph.
Yes. Yes, and it simultaneously can be interpreted as a space of states, but maybe a better way to think of it as you just said, Marco.
Okay,
So
thanks.
it's maybe a Lagrangian subalgebra or maximally commutative subalgebra in something better, but we were too scared about this better object. This better object would not be commutative.
Uh-huh.
Mhm.
I see. Okay, thank you.
So I think that's actually in line with how Schenkel and his collaborators define. So they have a recent result where they construct functorial theories and Lorentzian manifolds from algebraic UFTs, and they also take like algebras of observables as like states, state spaces. Like what they associate to an object is not like the space of states, but the algebra of observables somehow. So yeah, I'm just comes to mind when talking about this. All right, so okay, here's some comments on this that I partially already mentioned. So first of all, we are taking C infinity, not L2, and that's because, as I said, so L2 functions don't form an algebra, so they sort of don't fit into this scheme here. Like we can't really take consider them as sort of modules over themselves or smaller algebras, and also the pullback of a function, like these pullbacks that give us the maps between algebras, they don't land in square integrable functions because they're constant along some direction, so they can't be square integrable in the Lebesgue measure. Yeah. Then like we don't have cobordism hypothesis here. So we can't recover this functor from its values on a point, which would be just a C infinity function on that point or on highest codimension stratum. And actually the only interesting or the most interesting part is contained in this top stratum. So only the top stratum is the one that sees the metric. And that seems to be in line with like extended two-dimensional Young-Mills, which is another example that Pavel constructed together with a student, Ricardo Iraso, and which is also has been constructed, I think, in some terms of cobordism categories by Ingo Runkel together with the collaborator. So it seems to be a pattern that maybe somehow the metric, the interaction only affects this top stratum, but maybe this is also only true for like this example. I don't know. And okay, the last remark is that without the disjointness assumption, the resulting category would not really look like a cobordism category. Like it, you could like glue some weird things like this in this horizontal composition. So it wouldn't really look like a manifold anymore if you start with approximations of manifolds. So, okay, I have material for at least half an hour more, but actually I think I will have to go in a couple of minutes because my kids are going mental. I can hear them.
Okay, thank you so much for doing this.
Yeah. So
maybe we can, you don't have to answer now, but we can maybe continue on some other occasion. But thank you very much for this.
yeah, thank you, Marco. Thank you for all the questions and the nice discussion. So
we'll send you the link so that you'll have this recording for anything else you might want to use it for. Are there any other questions quickly that anyone wants to bring up now? Okay, so we'll try to have Konstantin back at some point in the next few weeks, and maybe you can we can study your notes. Would it be possible to send your transparencies to us so we
Sure,
can study
yeah.
them?
Of course.
Okay.
Of course.
Okay, great.
Mhm.
Okay, thanks, and thanks for everyone showing up. Thanks also to Pavel for assisting. That was very helpful. And thanks
Yes,
for
thank you,
thanks to
Pavel.
Maziar for organizing this. Okay.
Thank you for the thought-provoking questions.
No,
Yes.
hopefully we can continue talking about this material. I think these projects are really cool. I think you guys are doing an amazing series of works. Okay, yeah, thanks everyone.
Thank you.
Thank you.
Bye.
Okay. And